Ladies and gentlemen, please join me in welcoming our final speaker, Professor Yao Quanming. Professor Yao is currently a tenured associate professor in the Department of Electronic Engineering at Tsinghua University and a recipient of China's National High-Level Young Talent Program. He previously served as a principal researcher at Four Paradigm Inc., where he founded and led the company's machine learning research team. His research focuses on machine learning methods and principles, with particular emphasis on scientific intelligence and the theoretic foundations of large models. Today, he will present his talk entitled Parsimony Learning from Deep Networks. Let's welcome.
Thanks for the introduction. Okay, uh, today I will talk about perhaps some of recent progress in our group follow this principle, Parsimonious way in deep learning. First, my talk will basically cover three topics. First, I will talk about why we need to make deep network be more parsimonious. Then we will talk about our perhaps big idea and our principle to develop this type of technologies. And finally, I will introduce three recent works that reflect these technology and how they can be used in AI for science and how they can be applied for industrial applications. First, perhaps not a so long history compared with the development of math. Basically, okay, the development of AI perhaps starts from 80 years ago. And previously, the main message, okay, the big message is that, okay, first we may have feature discriminate. And later, we have some shallow networks. And perhaps 20 years ago or 10 years ago, we have deeper networks. And now, 8 or 5 years ago, we start to work with large language model. The most important message is that, okay, along with these gentlemen, the goal we always want to achieve is that we want to have, okay, this word. We always want to have larger model. In this way, we can have stronger representative ability. And empirically, notice that I say empirically. Okay, nowadays, the development of AI, somehow I need to say is far beyond basic mathematical assumptions. So previously, analysis for SVM and feature discriminate or decision tree no longer apply for large language models. So empirically, the larger the model is, and the stronger representation ability it has, and then empirically, we will have better learning performance. And so now, this week, NVIDIA has about 400 million US dollars on the market. So basically, to support its market value, its computational power, okay, we have big machine. And the data, 5 years ago, data is not a problem, but now data is a problem. Okay, we have big data. And finally, we have a very large model size. So this is the trend from GPT-1 to GPT-4. Okay, these are more recent typical applications that have been achieved so far by large language model. And this is typically reasoning benchmarks. And now, like, these benchmarks have already become too easy for current large language models. This figure is taken just from 1 year ago. So as you can see, like this value is 86, but now this value has grown to about 95. All these accuracy performance have been already achieved more than 19%. And okay, this last year's Sora and AlphaFold and ChatGPT question and answer application, typical application. So let's take a back to look at industrial application, industrial development for large language models. So this is the big picture in just 2 years ago. And this is the big picture we have, okay, last month. The basic trend is that, okay, we can see we have perhaps early bird, which is done by Baidu here, and this is done by Bloomberg, a large foundation model in finance area, and this next sense chat, and this is the Wu Dao too. But now, as you can see at this corner case, most of those large language models are from Google, Meta. Now, this is from DeepSeek and ChatGPT. So the trend is that small companies are gradually ruled out from this track. And what are remade are just, okay, those big companies, especially those companies can buy hundreds of 200 or 800 GPU cards. So basically, to support the development is, okay, this is a question I want to ask later. So with this trend, and actually these are the basic law to, perhaps this is not a formal mathematical law, but just an empirical observation with the computational scaling and with the data scaling, finally with model size scaling, we can expect that, like this is the test loss. The test loss decrease linearly. So this is what basically scaling law tells about. Once we have proper scale up the computational size, data size, and the model size, then if you sufficiently train your large language model, then you can expect your test loss on many subsequent tasks can decrease linearly. So based on this triangle law, okay, we can see these are some recent news happened in this week. This is about IMO. 4 days ago, ChatGPT says there are some internal news from ChatGPT says that their latest large language model 05 has already can achieve a gold champion in IMO's latest test. However, yesterday, okay, Google officially released their certification from IMO that their latest model can really achieve champion performance. And today, as if you see the latest news, those development help Google achieve the gold medal have already been recruited by Meta. So the competition between those big companies is very intensified. So in this way, we can see the performance grows continually. And actually, Grok 4 is done by Musk's AI company. And the latest performance from Google and ChatGPT 05 has not been reported here yet. So these are the recent news from this area. Okay. Typically, the message is that current large language models can achieve very good or impressive performance on web scale applications. But, however, okay, when we come to practice, when we come to real demand, we will face up with many other type of applications that cannot meet the requirement on web scale data. So typically, what drives our economy during past 20 years for web service is actually cold start problem. By cold start means that, like WeChat or QQ, we want to attract new users to use our service and to use our product. So if I were a new user on WeChat, then actually the system will have a few personal data about me. So this is the competition between two companies. This two company already has a very good foundation model, perhaps O1 or DeepSeek, but even build upon this good foundation model, they need to develop cold start techniques that to attract new users to use their own product. So in this way, this is the situation. We have only a few data, and you have a very strong backbone. And you need to compete with other participants to do stronger personalization to attract more new users to your own service. So this can be a problem because we only have a few data here. And actually, for healthcare, actually, the requirement is that when you find a doctor, okay, you want to ask him or her why I was ill. So he needs to give explanations. And actually, even with chain of thought, large language model can give you the clue how the final decisions are made. But actually, what happened during the message passing layer, especially in the attention layers, are not clear. So actually, if intrinsic explainable cannot be achieved by large language model, at least we want to know what happened, what message can be passed through from one layer to another transformer layer. So in this way, actually, we want to the control or the message passing process in those large language models can be more transparent. These are typically needed for AI for drug or healthcare domain. And actually, embodied AI is very, very hot this year. And typically in this scenario, we do not have such strong computational power. Actually, if you buy an embodied AI product, and this product tells you that it must be connected to the internet, then you can use it well. Then the product will not sell good. So basically, nowadays the demand is that with large language model empowered agent, they can be built alone inside this limited hardware. So you cannot really fed in a very big large language model on these edge devices. This model can only afford perhaps a 1 billion model, a model with 1 billion parameter size or even less. So this can be a big restriction for computational resource. And finally, actually, for application like DNA structure, the story is kind of different because even with recommendation, healthcare, and embodied AI, you can interact with the data in a way like humans. So you can express your need and demand by natural languages. However, for DNA structure, the coherence in natural languages may not appear in the DNA sequence. So while, okay, we can still take as the sequence data and fed into transformer. But how the interaction between different genes be captured, it is a problem. And even worse, for graph structure data, large language model does not have reasoning ability on such discrete data type. So this is actually what happened in practice as a short summary. Data problem, transparent problem, computational problem, and intrinsic data structure problem. In these applications, okay, you will see computational scaling does not apply, data scaling does not apply, model size scaling does not apply. So actually, these are the new chances for companies or for technologies that work or serve for large language model. In this way, okay, we will not see, if you build a company or service, maybe 2 years later, you will not be eaten by them. So this is a general trend that we want to work with and want to solve along with large language models. So this is computational scaling, data type scaling, parameter scaling. And if you continue the old story like scaling law to those embodied AI applications, actually this is what you will see in practice. Okay, this is the requirement performance you want to have in order to meet industrial need. And actually, if you want to continue the scaling law, okay, the curve will go flat because you will meet. This is the limitation, either by data or computational resource. So there is a big gap here. This means that we need to seek other way around to solve this type of problem. So actually, before we reach the final performance, the field exhausted before. The field like computational power or data source has already been exhausted. So this is why we want to work in a Parsimony way. Basically, it means that we want to achieve stronger performance in a more compact way. The compact means that we want to find essential things in the data or in the parameter. So in this way, we wish the development techniques can have less requirement on the data or the model size, and the inference process can be more transparent. Actually, this is a long. This philosophy started long time ago, even before the birth of our AI. Actually, Einstein talked about this. This is his philosophy 100 years ago, just a long time before the birth of AI. And now, the situation is that we have such a need to make large language model practical or useful in many other industrial applications. So we want to solve this problem, and we need to seek some motivations. Actually, we want to learn from the real world or the physical world. So, like in our cognitive world, when we just born, we perhaps can only see black and white and do very simple tasks. And when we gradually grow older, especially when we graduate from universities, our parents will expect that we can leave our home to earn some money to make ourselves live more comfortable. So this means that the ability or the task can be performed by human beings goes extremely complex. However, the activity of neural connection is more intensified during childhood. And actually, the process of learning and to recognize the real world is try to prompt your connection between your neurons. So actually, somehow, this basic message means that you have a very powerful brain at the very beginning stage age, and the connection gradually moves when you get older. However, your ability gets stronger. And for the physical world, even complex, very complex physical phenomena can be described by some physical equation or basic laws. So this motivated me to ask one question. So this is the question I always pursued during my research career. So are complex machine learning methods can also be determined or explained or governed by some fundamental simple principles or laws. So this is the basic motivation from complex world. And in practice, we want to make this idea develop to exact tactics can be used. So this is the basic idea. For typical domain, perhaps in embodied AI or recommendation system or healthcare, in this domain, we will have some basic rules or practice developed during perhaps 20 or 30 years of practice. These symbol or rules can act as just the building bricks to guide generalization in deep networks. So this achieved combinatorial generalization dual learning. And the basic things that we need to identify the building blocks or building bricks in this domain. And in this way, okay, given still the basic backbone like large language model, we can seek a clever strategy to improve the efficiency of data and to avoid exhaustive increase of computational effort. I will show a detailed applications later. So this is just a show a message, okay? We want to find a rule in this domain to use the rule to guide the reasoning process or the learning process in the deep network. In this way, we can achieve the desired performance before, okay, we have used out the computational resource or of the available data. So before ending this part, I want to show another message that actually it is possible. These two papers are done by Cambridge and Oxford. Okay, this is 2 years ago, and actually this is 10 years ago. Since this paper, future learning has been the second reference. Since the publication of the second reference, future learning has been a very hot popular in machine learning. And actually, this Nature paper 2 years ago says that, okay, given 3 or 5 layer MLP, if we use compositional meta learning, what it means by compositional? Okay, let's look at this figure. This is a model, and actually these are the basic component. That's the wheel and this stick. These are 3 basic components. These components together can make a motorcycle like this. So if we inject this knowledge into the meta training process, even 3 to 5 layer simple MLP can achieve stronger combinatorial generalization performance than GP3. So this is a very strong indicator that if we can insert proper knowledge into the model, or either like this meta training process in this paper here, then it is possible for us to achieve a very strong performance in vertical learning task. So this shows a feasible message. And actually, okay, in this figure, I grew up the development of Parsimony learning in 3 stages. The first stage is statistical driven. And actually, we will see many famous people here, like David Donoghue and Terence Tao, because they start comparison sensing in this area. And actually, in the second stage, these techniques have been gradually transferred to deep networks. Like Professor Mai also work in this area, and actually, okay. And based on his techniques, Han Song has introduced compression techniques into deep network. And actually, this paper is outstanding paper of iClear that year. And currently, because purely mathematics may not explain all happened inside large language model, so we need to bring wisdom from physical world. And actually, I call this stage is knowledge aware. So in this way, we can see that Nature paper is here, and those papers marked in red are done by our group. I will talk about some of them later on. So this is the big picture. And the research landscape in our group would work in this way. Okay, smaller data and a smaller model, less data, and more transparent reasoning. And these are representative works towards this direction. And finally, as a minimum demonstration, we will show how emerging can actually it is the first lower drug interaction. It's the first deep learning method that can make effective prediction for lower drug interactions. And later I will explain how it can achieve even better performance than GPT-3 at that year. I will just briefly mention those details. Okay, there are too many words here. Okay, this is the big picture, and actually in these columns we will summarize our ideas and the method. And previously I mentioned that we need to have a knowledge space, and in order to be processed by computers, we also need a functional space, like work with vectors and matrix to make it work. So these are what we have in the knowledge space, and this is what we have in the functional space. And this is the relationship between the knowledge space and the functional space, and how they can interact with each other to make stronger prediction. Okay, these are the brief summary. Actually, this big table are in our perspective, which published this year on AI Magazine. At the last page, I will show the reference. Okay, with the lead and a brief introduction of our research landscape, I will briefly talk about recent progress. The first is the minimum demonstration on emerging drug interaction prediction. And actually, this is a very typical application where we can only have a few data because, okay, severe adverse drug reactions will really kill a person. So in this way, it is naturally a data sparsity problem. However, for typical neural network, it is very data hungry. So in this way, we want to make deep network feasible on these applications. So we need to seek some helps. Basically, we will take this as a graph learning problem. Okay, this is a new drug, and this is an old drug. And we want to predict the link between a new drug and an old drug, and to predict whether the missing edges are an adverse reaction or not. And actually, this is the big picture of existing work in this area. Okay, this is the GPT-3, and this is graph transformer. Except these two, perhaps I can say foundation model, and actually this is classical method, MLP, and these are the graph neural network. So as we can see, the big message is that, okay, with foundation model, it can see many text messages, so it can have somehow good performance on new drug interactions, but the required data amount is very huge. And for simple baselines like MLP, the data amount is not that huge, so but its performance is very bad. And actually, our method, emerging, can achieve stronger performance than foundation model, but with only require a few amount of data. So the basic message is that for drug development, we can actually have many more scientific background, like what disease such a drug, the drug fall in those compounds here and can cure, and actually what side effect and what gene it can be targeted. So perhaps this drug can be new, but it can target at the same gene as an old drug. So this can serve as a background knowledge for us to predict, to have some weakness supervised knowledge to give stronger performance on those novel drugs. So perhaps let's just look at this architecture. So this is the background knowledge biometric network can contain synthin and gene. And this is the DDI network. We have a new drug and an old drug. This is a new drug and this is an old drug. So as we can see in this figure, long drug and this drug can share a same synthin. So this can be provided as a weakly supervised signal. So basically, we will, based on this augmented graph, to extract common paths from U and V. And along this common path, those nodes will be the common gene or common target. These two drugs will have in common. So in this way, we developed an edge we developed a customized graph neural network to utilize those weakly supervised information to give stronger prediction. Okay, well, due to the time limitation, I will jump those details. So as a performance comparison, we can see this is the graph transformer, and this is the large language model based on GPT-3. The paper published as in fall of 2023. So at that time, we can only use GPT-3. And last work, we will compare with the latest DeepSeek model. Okay. Here, as we can see, emerging can achieve better performance than GPT-3 and a graph foundation model. And actually, if we compare graph neural network and those simple model, we will see, okay, GNN may not have stronger performance than, okay, drag feature. This DF means drag feature. So every time we want to achieve better performance, we need to sacrifice something. So we have indeed more parameter in GN than deep feature. But in order to activate the expressive list power in graph neural network, we need the field. The field is more data. So if the field is not enough, so it can achieve even worse performance than simple baseline. Large language model can have already be pre-trained on many text data. So it somehow can have some common knowledge on that drug. So somehow it has relative good performance. Then on the parameter size, this is the comparison. Okay, actually this is our model, and this is the backbone we explore. So actually we can see of 0.5 percentage parameter compared with large language model. So the data is very, very small compared with this one. Finally, I will talk about how explanatory paths can be identified by our model. So basically, we have this subgraph. This is the new drag, this is the old drag. And these are all entries in the biometric network that two drags can interact, have common. So we have designed an attention mechanism that can help identify the paths, okay, which have the highest attention weight. So these are two examples, the blue one and the pink and the red one. Okay, these are two paths that along all possible ones that have top two highest attention weight. And we will put those paths into like Web of Science search engine. We will check what the search engine will return for us, and we will check whether those tags returned can reflect this new interaction can be made or not. And actually, we can identify that nearly 60 to 70% of those identified paths can be expanded. And finally, we will look at the correlation between, okay, one row means that DDI in a label in the DDI network, one row here. And one column means the relation in the external biomedical network. So we want to see what type of interaction in the biomedical network that can really boost the prediction performance for given DDI. And actually, there is one specific, okay, relationship in the biomedical work that can nearly consistently boost the prediction performance of all DDIs. Actually, this really makes sense. CRC after checking the data set, original data set, we found that CRC means resembling, means that how one drug looks like another drug. So if two drugs are exactly the same, so their reaction pattern will also be exactly the same. So this way, this explains why CRC can consistently boost the prediction performance of nearly all interaction types. So this is what can be discovered by our model. So this is a very short summary. Like Parsimony GN, this is what we developed. It has low training cost. compare with large language model and the very few data requirement, and also compare with these two model, we have stronger interpretable ability. Built upon this work, we develop a hybrid method which can explore potential of large language models. At this work, we only work with graph neural network. Here, we want to achieve a Parsimony development with large language model. Okay, this is the brief introduction of VDI one drug and another drug. We want to predict their reactions. And here, the motivation is that if we want to find a doctor, and if what I want to seek the feedback is relative liu for her, and it is very likely for her to look at the past patient he has already taken care of. So this motivates us to seek a case-based reasoning approach. So this is actually the classical pipeline of case-based reasoning. We have a knowledge base, and if we have a new record, okay, like a new case, the system will first retrieve historical similar cases and reuse it to predict, to explain something, and then revise this new case. Finally, feed the new case back into the repository. Actually, this system is very popular in 1970s, where IBM have developed a diagonal system use knowledge base. And at that time, the case base is knowledge base. So this is a very, this case-based reasoning has a very long history back into the AI development. And the basic message is that, okay, for DDI, like the existing DDI pattern can be seen as cases. And like large language model has the ability to somehow to understand this case. However, large language model can only understand can only understand the text message in an exact way. So we want to use the graph structure data like DDI to help the reasoning process inside the large language model. So this is what we want to do. Actually, DDI cases can share common interaction mechanism, and we want to use the ability of large language model to understand text data to reveal or to identify this interaction mechanism. Notice that DDI data alone does not directly record those interaction mechanisms. We want to use large language model to identify this mechanism by itself and use this mechanism to revise the DDI, the record DDI, and to push it back as a case to the knowledge base. So this is our idea. Transfer of known interaction mechanism from historical cases to the new one. And this is our framework. So basically, this is the naive case-based CBR. CBR means case-based reasoning method. We have drug 1, drug 2, and a simple retrieval and a database, and then similar cases which has a similar DDI pattern like given these two drugs, and directly fed into large language model and give an output. And this is our method. The first thing is that we have an external biomedical KG, like it contains gene and small compound, like the, okay, this is just this one. This one has side effect compound, this. This is the accumulated database in this area. And we directly take it as a background or original knowledge source. However, we do not directly multiple edges or paths. We want to use a GN as a clever reasoner to find really important drug associations, put it into the knowledge repository, and use large language model, use this revised revised record, and take this and use combine LM and this revised record to find the cases that are really important for the current drug interaction pattern, and then put this drug association and refine the cases, and reuse large language model again to do the final prediction. So it contains three parts: case retrieval, use a G and a large language model to retrieve the really important drug associations, and reuse these drug associations to activate large language model intrinsic reasoning ability to give the final output. So the most important thing perhaps is how to design the case. Okay, it looks as follows. First, we have a drug description. Okay, what basic information are these two drugs? And then we will identify, these are identified by the graph neural network, important drug associations. And okay, interaction mechanism, that is, this part is directly generated by large language model. So this is the interaction mechanism that is identified not in the original data, but by the large language model. Finally, give the prediction on the interaction type. So this is what we stored as cases in the knowledge base. With this case, okay, this is how we implement previous pipeline. Okay, we have a hybrid retrieval mechanism, and also this is a knowledge guide reasoning process. Okay, I will, due to the time limitation, I will jump these details. And as a comparison with closely related works, okay, this is a text DDI, which is also done by our group, and this is the recent work by 北医三院, okay, DDI GPT, 北大和北医三院, okay, and this is naive GCBR DDI method, and this is actually done by Cambridge University, and this is our work. So we can see without fine-tuning and interpretability, and we can mine proper drug associations. Finally, we can summarize interaction mechanism and put it back to the knowledge base. What interests the most is the performance here. So as you can see, indeed, if we believe that stronger or larger language model can have better performance, okay, but you need to do it in a clever way. As you can see, indeed, for the base means that we directly use llama, 8 billion, 70 billion, and 671 billion. Okay, this is really large. So you can see as the base performance can indeed increase. Okay, and the increase, even the performance is increased, the final performance is still very bad. And as you can see, base model plug with naive CBR can significantly improve the prediction performance. So this means that in this vertical domain, the accumulated historical message is really, really important. And combined with our method, okay, we can see the performance is significantly increased. This is the first observation. And the second observation is that, okay, with the carefully designed gene as retrieval and reasoner, we can see we no longer need such a big foundation model. As you can see, okay, perhaps 8 billion, okay, performance is good enough because the performance is not that huge compared with, okay, like the performance improved here. So in this case, actually in most vertical domain, if you really care about, like here, AI for drug task or some scientific or math reasoning task, you perhaps do not really need such a huge language model. Okay, this is the the output example by our model. As you can see, historical case, drug association, and faithful output. Finally, I will talk about one understanding towards why large language model can work so well. So as all of you have already commonly perhaps used Gemini or DeepSeek, okay, this is what typically we will use. We will give some demonstration and leave a blank here and ask the large language model what's the answer here. So actually, this is a very typical future learning setting. We have 3 examples. We need to make a prediction. So personally, feeling is that, or our personal feeling is that large language model is a very good future learner. As you can see, this is more detailed performance analysis. So empirically, large language models are very good future learner, but why it can be so good? So in this paper, we want to answer this question. Just a small attempt. Why large language model can be good? So the basic method is that we want to learn from past machine learning classifiers. Like this is what we look at, classical meta-learner. Like this is the metric-based and amortization-based and gradient-based. This is the MAMO, this is the prototype network, and this is the hyper network. This type of tactics has already been developed more than 30 years. So these are the typical machine learning algorithms that classically be dealt with future learners. So can we learn something from these past good examples? Can this be used to explain why pre-trained large language model why these pre-trained LMs can be so good? So this is our motivation. And actually, we have established a mapping or connection between ICL and classical learning algorithm. And actually, due to the time limitation, I will not talk about those details. Actually, this paper has been already published in iClear this year. So if you are interested in details, you may just refer to the original paper. So the conclusion is that, okay, this is the hypothesis of metric-based learner, and this is the hypothesis of gradient-based meta-learner, and this is the amortization meta-learner. They are not exclusive with each other, so they can get overlapped. And actually, ICL is stronger enough to express all these existing meta-learner. And not only existing one, but can also generalize to some other ones that has not been designed by hand previously. So the conclusion is that ICL is expressing enough to imitate existing meta-learner, and it can also be further driven by data. So this is some simple experiment result. These are some ground truths generated by hand-designed meta-learner, so like PhotoNet, MatchNet, and CNAPs. And as we can see, if we train ICL in a way, it can match the best ground truth. And if we design a hybrid approach, which means that we generate the ground truth by prototypical network and the MatchNet, in this way, low single ground truth can work best, and it can still identify the best. So ICL learns the optimal algorithm beyond the typical meta-learner. Finally, actually, it can generalize to unseen tasks. This is also what we typically expect with large language model. Okay, finally, these are the works that are covered in today's talk. And finally, thanks to team members and students in our group for these fantastic works. And this is the end of my talk. Thanks.
Okay, very nice talk. So since the time is limited, we only have one short question. Any questions? Okay, I will ask a very short question. You just mentioned to use graph embedding to retrieve from the database. So since the organic function is related to the substructure of the molecules, so I'm wondering whether the hierarchy embedding of the molecule can work better.
Actually, okay, uh, the embedding is not the, actually the gene is work on the big Lorentz graph. So the embedding is not the embedding of the molecules. Actually, we want to retrieve the cases from the large repository. So the embedding is just, okay, text.
Okay,
So not the graph embedding.
okay, okay.
But in order to fill in those blanks, we need to use GN to find entities. And once the entity is found, fill in those blanks and take the text embedding to retrieve similar cases.
Okay, I get it. Thank you.